Welcome back to the shrine. Just when you thought that YouTube needs one more do-it-yourself homemade kiln video, here's my take on it. This is a Mako electric kiln. I purchased it on an auction more than 10 years ago, knowing that one day it's gonna be handy. As you can see, it came without a controller. So this is the pedestal for the controller, but it is missing. The kiln itself has a almost 10-inch by 5-inch opening, and inside you can see the coils. So there's a set of coils on this side, there's a set on that side, and this is the temperature sensor inside. It's pretty well built and it's fairly heavy, and on the back here there is just a panel. You can see the wires coming out right there. So this is one set of coils, that is another set of coils, and there's just a junction box here. I attached a plug to it and I tested it, and here's what I found. The kiln was drawing about 17 amps when it's cold and about 10 amps when it's hot. Again, it's got two coils connected in parallel, and this is what I'm about to do. So I'm gonna have a PID controller looking after the thermocouple, and then based on the feedback it is gonna switch a solid state relay on and off. And I'm gonna have the whole thing on this switch, so that the switch is going to turn on the PID controller and the SSR. And I think that's necessary because the SSR might have some leakage current, and all it's gonna go into an AC plug, and I'm gonna put a grounding on it. So these are the components that I obtained so far. So this is a PID controller manufactured by Fuji Electronics. This guy goes for about $1,000 on eBay. I salvaged it from an LOM machine. This was my old LOM machine. It was a 3D printer, and I basically sold all the components. But this guy, I kind of knew that this will become handy one day. I also have the solid state relay here. This is a 40 amp. You can see that the range is 24 to 380 volts AC, and then on the input it's 3 to 32 volts DC. So this is going to control the coils, and I got a box. It's a nice project box that will house the components. I also have a DP/DT switch, and this one is rated, you can see 20 amps at 125 volts AC. So this should be plenty to switch that coil on and off. So the first thing is to kind of figure out where we're gonna put this PID controller. So here's the box. As you can see, it nicely fits on this pedestal. Probably this is where the original controller sat in the past. So the box can be mounted right here. I can cut a hole on the front, and that will house the PID controller, and I can populate this switch on the inside. As you can see, you know, there are some openings here on the front and the back, so you might imagine that air is passing in and out in this way. So the best way would be to install this guy in a vertical manner, so that when the air comes through, it is scrubbing by these heat sinks. Now the problem is that this guy, you can see as tall as the box. I didn't get a tall enough box, so I'm gonna put it sideways like so, and hopefully I'm gonna have enough room in the box for everything. So let's go ahead and start cutting some metal. Houston, we got signal. Got it wired up. You can see it's plugged in. That is a 12 gauge 3-wire cable feeding the switch, which is feeding the SSR, and it's feeding the controller. You can see it's set to 90 degrees and it's flashing the light. Here's a thermocouple. You can touch the end. You can see that when I'm touching the end, it reacts hot. And you can see when that happens, it's gonna shut the light off. The light is not on. So the controller seems to be working. A couple of things I screwed up. I used these tiny little connectors that come in a kit for, you know, a 14 gauge wire, 12 gauge wire. And I don't like that these wires are 14 gauge, so I'm gonna go and use 12 gauge instead. And I went ahead and bought these connectors. They are a little beefier. $5 for 5 connectors. That's a steal. And I also needed cable. Well, guess what? The 12 gauge cable, a 50-foot roll, is $25. And this hookup cable was only $13, and it has enough cable in it, and also it's colored. So I can hook up the solid state relay to the kiln, and also I'm gonna have some cables for inside the box. As you can see, the entropy is at its peak. The machine is all assembled, and I did some testing, and the temperature shown by the PID controller wasn't the same what the data acquisition device was showing. I actually had a standard K-type thermometer here. As you can see, just stuck it in a hole right there. And I also used one I purchased from China, this one, and they showed the same temperature. Now I was suspecting that this one might have been connected backwards. Double check that wasn't the case. Here's the one that's made in China. You can see it works from -50 to 1300 C, and it's a K-type thermocouple, so it should work fine with this PID controller. Here is the original one from the machine. I removed it yesterday, and as you can see, this has seen better days. So these are the original contacts. Look like someone didn't like it. I think it might have failed. You can see how it was just wound on the original one. So the task at this point is adapt this one to the kiln. But as you can see, it doesn't fit through the hole. So first thing is first to increase the hole size, and then create some kind of bracketry to hold this in place. There you go. Fits like a glove. So here's the thermocouple wire. As you can see, there's a red and a yellow. And I'm just gonna go and cut the ends off. Just introduce some new copper and then put terminals on it. There you go. So on the thermocouple, as you can see, it's clearly marked. There's a positive and negative. So it's essentially just two different types of wire welded together at the end. And so the type of the wire will define if it's a K-type or, you know, whatever type thermocouple it is.
System startup 11:02. $43°, that is Celsius, set to 1000. And this is just a control thermometer. It shows 35.57. It's raising, and we're gonna go into record mode. So now it's recording the rate with which it will start up and heat up. 12:05, it's raining. As you can see, the controller is at 632. It's going to 1000 C, and I have another control here, and it's at 633.4, and it's still going up. So both the thermocouples are showing almost identical values. It's 19 past 1 o'clock. It's raining outside. You can see 72, 80 inside with the windows open, because I've got a huge heater going on. 870 degrees Celsius as shown by the display. Yeah, 130 to go. And this one is the control. It also shows 872. And in the meantime, I realized there's some leakage here. So you can see the plate right there is bent, and so it's not allowing the door to completely close. So that is something I'm gonna need to adjust. I also, if I'm touching the controls here, I can feel the heat coming out, and it's not necessary from this box. So I'm gonna have to move this box all the way to the back, because there's leakage heat coming out this way, and it might be affecting the box. 3:08. So 4 hours after I turn it on. 968 degrees. And this one shows 972, so it's fairly uniform. I say that the two thermocouples show about the same temperature. You can see I just fed this thermocouple cable, and then it's on the end of a long rod when I inserted it, and it might not be in the same temperature. Also, I saw that there's a bend in the metal structure here, and because of that the door does not close completely, so there's a lot of leakage of heat coming out. But nonetheless, I mean, 968 degrees, that's enough to melt aluminum and almost enough to melt copper. I got a thermal camera going on here. This is gonna be interesting. There you go. So here's my thermal camera. I'm showing you live footage. You can see that a lot of heat is coming out through there, and it just shows that it's more than 150 C. The box itself is about at 60 C, right, those openings are about 60 C. The top of the box is showing at 50 degrees. And then notice here's the cable. So you see the cable goes into the wall, and it is showing that cable is about 30 degrees C. So the cable where it's plugged into the wall gets fairly warm. I wouldn't call it hot. But the kiln itself shows up piping hot on the video feed. Let's look at the back. So here's the back. You can see there's not much heat leaking out. Most of it is leaking out in the front and also underneath there. So you can see there's some leakage. And then this back cover here is cool, so right where the wires are, it is staying pretty cool. You can see the wire nuts, so there's a wire nut. You can see the wire nuts are relatively cold, which is good. As far as inside the box, you can see it's around 50 degrees on the outside, and on the inside it might be a little bit hotter. So I'm gonna go and turn it off. When it cools back down, I'm gonna straighten this edge out so I can completely close the front door. And then inside I have a piece of metal. So let's go and take out this thermocouple. Okay, let me shut the light. You can see that it's red hot, and whatever surface finish coating was on it completely burnt off. I think this was zinc plated. This was a piece of a rod that was originally a damper. So I'm just gonna set it aside like that. And I put a random piece of steel inside. Ow, ow, ow. It's hot. It's freaking hot. There you go. A random piece of steel, 960 degrees. It's hot enough to melt aluminum. So with that, that's gonna be a wrap. That was a successful reborn of the Ameco Kiln, whatever the pronunciation it is. It might be AMACO, electric kiln. Looks like the controller is working. I need to do a couple small changes to it, but overall it was a success. I'm glad you guys joined up for the ride. Hope you enjoyed the video, and see you next time. Bye. That's a red hot piece of metal.